Okay, so now we want to use the Rayleigh quotient to get an upper bound for the lowest eigenvalue of this equation here. Okay, so I guess two things. One, let me write out what the Rayleigh quotient is, and once I do that, then we can talk about the best trial function to put there. And I'm actually to write instead of writing everything out again, I'm going to be a little bit lazy. I don't even know if this is worth it, but I'm going to go to the let's see, the Sturm Liouville section. Let's see, where do I have it? Is it here? This is it. Okay. Well, where is it? Where did I put it? Oh, it's going to be back on Sturm Liouville 1, isn't it? Okay. I thought this would be easier and more less boring than watching me type it, but now I can't find it. Okay. I think this is going to be it. Okay. Let's go back down to the homework. Okay. The Rayleigh quotient. This is it. So let me just see if I got the right thing here. Well, that's not the form that we wanted, is it? Here we go. This is what we want. And we're going to be able to simplify this greatly due to the boundary conditions. Whoops, that was a... Alright, we have this. Oh man, come on, dude. Here we go, I need an equal sign. Okay. Okay, so the Rayleigh quotient, this is it, except I want to change all of my phi's here to u. So we're going to have u, and then u prime, and then we're going to have a u prime here, and a u here. Oh, and this will also be a u. Okay. So let's go through and replace things. If I look at my boundary condition right here, u prime of 0 is 0, because remember, when we use the Rayleigh quotient, we put in the minimum. So the theorem says that the lowest eigenvalue is the minimum of the Rayleigh quotient, where the Rayleigh quotient, where that minimum is taken over all continuous functions that satisfy the boundary conditions. So u here has to be a continuous function that satisfies the boundary condition for the Rayleigh quotient thing to even make sense. Okay, so we're going to put r of u here. U prime of 0 is 0. So when you plug in a, which is 0, you get 0. U of 1 is 0, so that's going to be 0. So the boundary terms are 0. And this a should be a 0, and the b should be a 1. 0 and a 1. Okay, let's try to think about what the other things are. Phi double prime, so p is just going to be equal to 1, so I can get rid of the p. Now, what is q? Well, q is going to be equal to minus x squared. Remember, it's phi double prime plus q phi. So we've got q then is going to be equal to minus x squared. So q is going to be minus x squared, so we're going to have plus x squared. And then sigma, that's the thing multiplying lambda, so sigma is just going to be equal to 1. And so we have this. Okay. All right, so this is what we have here. Now, what I want to do is I want to think about what the first eigenfunction is going to look like. We know that, from the theory, we know that the first eigenfunction is not going to have any zeros in the interior of the interval. So For example, it could be 0. In fact, it is 0 at 1. It could potentially be 0 at 0, but it can't be because phi prime of 0 is 0. I'll explain why it can't be 0 at 0 in just a minute. And it has no other zeros in that interval. So it's going to look, something like that. The graph is going to look something like this, which, is like a trigonometric function just, going like that, or like an upside down quadratic, like a negative quadratic. Now, the thing that we want to get, so the u that's going to come closest to minimizing this is going to be a u that is, like, the closer u is to the actual function in terms of its integral. So the closer u is to the first eigenfunction. In other words, so just the closer that u is to the first eigenfunction, the closer this is going to be to the first eigenvalue. Okay, so I'm going to try a couple of things here. Let's try, and I'm going to give my explanation here because I haven't worked out this problem yet, or I have, but I did it a while ago when I first did this. When I first wrote the homework assignment, and that was all on pieces of scratch paper at my house somewhere. Okay, so let's try to find a function of the form, let's say we're going to. Let's find a function of the form ax squared plus bx plus c that satisfies the boundary conditions and has no zeros in the interval 0 to 1. Okay, now of course u of 1 should be equal to 0. Let me call this u of x. And here a is going to be a negative. I'm thinking about it doesn't have to be, but I want u to be a positive. So a is going to be negative so that we get a downward facing parabola. Now, actually, let me write this in kind of this more standard form. It'll be more helpful. So I'm going to write this as a times x minus r squared, and then plus b like this. Okay, so now we want a of 1 to be equal to 0. We can read out exactly what the a's are here. So let's just do it this way. We want 0. Yeah, u of 1 is equal to 0, 0. Whoops, 0 equals u of 1, which is equal to a times x minus 1 squared plus b. Sorry, not x minus 1. 1 minus r squared plus b. So then this tells us that we could write it in the following way. B is equal to minus a times 1 minus r squared. So then u of x is equal to a, and then times is going to be x minus r squared minus 1 minus r squared. Now what's going to happen if x is equal to 1? We have 1 minus r squared minus 1 minus r squared, and that's equal to 0. Okay. Also, you want u prime of 0 to be equal to 0. So 0 is equal to u prime of 0. If we take a derivative here, if we take a derivative over here, what's going to happen? So the derivative of x minus, so the derivative of that part is going to be equal to 0. The derivative of this part is 2 times x minus r. So the derivative of this is 2 times x minus r. So we're going to be a times 2 times 0 minus r, which is equal to minus 2ar. Okay. So if a is equal to 0, it's no longer quadratic, so I guess that means r is equal to 0. All right. So then u of x is equal to a times x squared minus 1 squared. Or this is a times I don't know if it's good to write it as x minus 1 times x plus 1. Let's just make sure the derivative at 0 is 0, because this doesn't look right. Yeah, so if we take the derivative here, we get 2ax. We evaluated that at 0, we get 0. Okay. So we have a times x minus 1 times x plus 1. Okay, so this is going to be 0 at 0 and minus 1, and its derivative is going to be equal to 0 at 0. Of course, this makes sense. We have a parabola like this, and it's 0. You know, it's a parabola like this, where my finger's meeting, that's the y-axis, and so it looks like this. And so it's 0 here, and the derivative is 1 there. And I'm just going to take, well, so here's what I'm going to do. Any function of this form, okay, is going to satisfy a of 1, or sorry, any function of this form is going to satisfy u of 1 is equal to 0. So any function of this form will satisfy u of 1 is equal to 0. Because if you plug in x is equal to 1, you get 0. Whoops, what the heck happened there? In addition, any function like this, if you look at this formula right here, for example, if you take the derivative, you're going to get 2ax. You plug in x is equal to 0, you get 0. So any function like this is going to give us a continuous function that satisfies the boundary conditions. In addition, if we think about what happens when we plug it into the integral over here, when I do u prime squared, well, the a is going to get squared. When I do u squared, the a is going to get squared there. When I do the u squared there, the a is going to get squared. So whether or not I have the a is going to cancel out. So choose a is equal to 1 and u of x is equal to x. I'm just going to write it as x squared minus 1. We choose a equals 1 because that, we choose a is equal to 1. We choose a is equal to 1 because that will, we choose a equals 1 because the a cancels out in the quotient. Okay, so now you're going to get to see me compute some integrals here. Okay. Alright, so we'll first do the integral from 0 to 1 of x squared minus 1 dx. I'm going to line it up right here. Okay, so what is this going to be equal to? Well, when you do the integral of x squared, you're going to get, from 0 to 1, you get 1/3. And then when you do the integral of 1, you get 1. So this is going to be 1 cubed minus 1. So notice, of course, I mentioned u of x being positive, but actually in my my drawing, my motions here indicated that it was positive as well. But really, it's negative like this. We could pick a equals minus 1, I guess, if we wanted to. Okay, I'm actually going to go back to do that. I'm going to go back to do that because I want to have it to be positive. Okay, 1 minus x squared. We choose a equals minus 1 because the a cancels out in the quotient. So we compute this. I just think better for some reason when it's positive. So this is going to be 1 minus 1/3. But 1 minus 1/3, this is 3/3 minus 1/3. Whoops. So that is 2/3. Okay, now if you look at the integral from 0 to 1, okay, we're going to do u prime squared. Okay, so u is 1 minus x squared. U prime is minus 2x. You square that. Sorry, let's start over. U is 1 minus x squared. U prime is minus 2x. You square that, you get 4x squared plus x squared. You know what? Let me do this. Let me do this in 2 steps. No need to do it all. Okay. So now 4x squared. Well, x squared going from 0 to 1 is 1/3. We just did that. We multiply it by 3. we get 4/3. Okay, and now the last one is going to be kind of the annoying one, only because it's not going to give us a third. Whoops. It's going to be x squared times u, so it's going to be x squared times 1 minus x squared dx. Okay, and what is this going to be equal to? Well, I've got the x squared times 1, that's x squared, so that's going to be 1/3. Let me make sure I have that correctly, yes. And then x squared times x squared is x to the power of 4, so this is going to give me 1/5. Okay, and now I'm going to need to get everything, let's say, in terms of 15ths. So I need to multiply this. I'm going to need to multiply 2/3 by 5/5, so this is going to give me 10/15. So I'm going to get 2/3 is equal to 10/15. This is equal to 20 over 15. And then this is going to be equal to 5 minus 3/15. So we got 2/15. So then all right, R of u is equal to, okay, so this is the bottom, so this is going to be 10/15. I probably could have kept that how I had it. And now we're going to have 20/15 plus 2/15. Now, of course, all those 15s are going to cancel. So then we're going to have 20 plus 2. So this is going to be 22 divided by 10. We can write that as 11/5. Now, we haven't learned about this. We haven't talked about this yet in class. But there's ways, I'm going to get this slightly wrong. There are sort of asymptotic expansions for the eigenvalues. Of course, when we say asymptotic, I'm talking about the large eigenvalues as we get bigger and bigger, and we're looking at the smallest eigenvalues. So asymptotic expansions, in that sense, don't necessarily apply. But the basic idea is that the kth eigenvalue for this problem is going to be really close to the kth eigenvalue for the case where x squared is equal to 0. It's called the free case. Now, if you solve this, if you set x equal, if you get rid of the x squared and you just solve the normal Sturm Liouville eigenvalue problem, you get that the eigenfunctions are going to be the cosine eigenfunctions, and you're going to get that it's going to be cosine of square root of lambda x. Square root of lambda is going to be equal to k pi plus pi over 2. So then lambda is going to be roughly equal to k pi plus pi over 2 squared, starting with k is equal to 0. Okay, so roughly speaking then, the kth eigenvalue for this problem is going to be pretty close to the kth eigenvalue for the free problem plus the average value, that is plus the integral of x squared from 0 to 1, and then there's going to be plus the error term. So what this says is that our first eigenvalue then should be around pi over 2 squared plus the integral of x squared, which is 1/3. Now, this is not asymptotic expansion. This is the very first eigenvalue. So in a sense, these really shouldn't be exactly close to each other, but this is the general idea. So if we do pi over 2 squared plus 1/3, we get 2.8. And now 11/5, what is 11/5 equal to? Well, it's 11/5 is 11/5 is 10/5 plus 1/5. 10/5 is 2. 1/5 is 0.2, so this is equal to 2.2. And this is right around, well, what did I say? 2.8 is what the asymptotic expansion says. Okay, so now what this says is that the lowest eigenvalue that we can come up with, what this says is now we know the maximum the eigenvalue can be is 2.2. So the maximum the eigenvalue can be is 2.2, which is better than our asymptotic estimate, which gave 2.8. Because remember, the lambda 1 is a minimum of R of u. So we computed 2.2. So maybe we picked the exact right eigenfunction here, and the eigenvalue is exactly 2.2. But whatever the eigenvalue is, it has to be less than 2.2. Okay, now this is not completely. What I'm about to do is not necessary at all, but I'm going to do it just because I think it's interesting. We can compare. So one thing that you can do along the lines of this, when I talked about how there was the asymptotics with the free case, if you choose an eigenfunction, one way to, so the question is you have to pick which function to put in here. Well, one idea is to get rid of the potential, make that q, and just look at the free case. We can compare with the free case of phi double prime plus lambda phi is equal to 0 with the same boundary conditions. And again, the reason is, and this is not something that we got to in this class, all of the spectral stuff, for a problem like this, it's a little different. It's a little different if you don't have a p. It's a little different if p is not 1 and sigma is not 1. But for a function like this, all of the spectral data, that is the eigenvalues and the eigenfunctions, converge pretty quickly to the spectral data, that is the eigenvalues and the eigenfunctions, for the case where q is equal to 0. Okay, so then it makes sense to set q is equal to 0 and then look at the eigenvalue, or find the eigenfunctions in that case, because asymptotically, again, not necessarily for the first ones, but asymptotically they get closer and closer, they converge to each other. That is the eigenfunctions for the eigenfunctions for this converge to the eigenfunctions for the case in which x squared is equal to 0, or the case in which q is equal to 0. Okay, in this problem, with the same boundary conditions. In this problem, that is u of x is equal to cosine of pi over 2x. Okay, and if we plug in x is equal to 1, we get cosine of pi over 2, which is, of course, 0. If we take a derivative, we get multiple times sine of pi over 2x. We plug in x equals 0, that gives us 0. So it does satisfy the boundary conditions. And notice there should be like a multiple here, like an a or something. But again, when we put it in the Rayleigh quotient, it's 0. So we're going to compute. Okay. I realized I was not recording. I don't know which part was recording. I don't know if it was when I was doing Wolfram Alpha to do these computations. At any rate, okay. So just because I'm lazy. So sine squared here, that's also going to be, if you just look at the sine squared, that's going to be 1/2 times pi squared over 4. This is now pi squared over 8, because when you do this integral, you get 1/2. You multiply it by pi squared over 4, you get 1/8. Okay, and then finally, 0 to 1, we're going to have x squared times cosine squared, so cosine pi over 2 squared dx. What are we going to get here? This is x squared cosine squared. So this is going to be 1/6 minus 1 over pi squared. So this is going to be equal to 1/6 minus 1 over pi squared. What a great denominator we're gonna have to deal with there. Okay, you know what? What I'm gonna do. Okay. All right. So r for this u is going to be equal to. This is going to be let's say pi squared over 8. So pi squared over 8 plus 1/6 minus 1 over pi squared, and we're going to divide this by 1/2. Or that's going to be 2 times everything that we have up here. Just trying to find the easiest thing to plug into my calculator at this point. Okay, so when I take this and multiply it all by 2, what am I going to get? Pi squared, that's going to, if I multiply that by 2, that's 4. If I multiply that by 2, that's 3. And if I multiply that by 2, that's that. Okay, now what is this going to be equal to? Pi squared over 4 plus 1/3 minus 2 over pi squared. Oh, this is right. This gives me 2.59. Okay, so this gives me 2.60. Okay, so this is worse. So this is a worse estimate. I'm actually wondering if I've not done something wrong, because I would have expected it to be a little bit better. Or at least not that far off. What's going on? Okay, so let's see here. Cosine squared pi over 2x, that's what goes in the denominator, right? Cosine squared pi over 2x, that goes in the denominator. Pi squared over 4, so if I take the derivative of this, so I'm now computing the numerator, so u prime squared. So if I take the derivative of cosine, I get pi over 2, well, minus pi over 2, sine pi over 2x, so I square that, I get pi squared over 4 sine squared. So let's go back just to double check this. This should be, I mean, this is 1/2. I don't know why I'm having to check this. So that's pi squared over 4 times 1/2 gives us pi squared over 8. That seems right. And then x squared cosine squared. That was the one that gave us 1/6 minus 1 over pi squared. X squared times cosine squared. All right, I put that 1/2. Okay, so the 1/2 comes at 2 eighths. Okay, 4, 3, 2. All right. I know this is fun, isn't it? Pi squared over 4 plus 1/3 minus 2 over pi squared. Yeah, 2.60. Okay, so we've got two different estimates, 2.2 and 2.6, and it actually turns out that this is the correct, this is the better estimate. Okay, so this was just to show you that we do it twice. I was hoping this one would be a little bit better, but it's actually a little bit worse. And so we know that the lowest eigenvalue is less than or equal to 2.2. Yeah, okay, I think that's sort of all I want to do for this video. This was a really long one. Sorry.